All right.
Good.
Then we're ready to get started. Hello, everyone. Good morning. Thanks for joining. Very excited to be here. I'm going to present the third lecture in our series on geometric deep learning with the topic geometric priors part 1. Joan will do part 2. So in this lecture, we're going to look at or take a bit of a closer look at some of the geometric priors, namely symmetry and scale separation, that will allow us to better tackle these dimension cursed problems. And specifically, we're going to take a look at some of the underlying mathematical ideas, such as groups, representations, invariance, and equivariance. So the outline for today is that I'll first discuss the notion of domains and signals, domains being things like grids, graphs, manifolds, and so on, and the signals being the data that lives on those domains. Then I'll talk about symmetries, various ways in which symmetries appear in machine learning in general and in geometric deep learning in particular. We'll study some of the mathematical concepts like groups, group actions, and group representations, and how this group acts on the space of signals. And then we'll talk about how to use this in deep learning using the concept of invariant and equivariant functions or network layers. So let's begin with a quick recap from the last lecture by Joan, where we talked about learning in high dimensions. So we saw that in general, learning, meaning in this case supervised learning, in high dimensions is intractable. The number of samples grows exponentially with dimension. I think we all know this. In geometric deep learning, however, that we don't just deal with generic data, arbitrary distributions of points in a high dimensional space, but our data are typically signals on some kind of space. And because of this fact, and because these spaces and thereby the spaces of signals have certain structure, learning can become tractable via the principles of symmetry, which I'll cover in this lecture, and scale separation, which will be covered in the next lecture. So also remember that as Joan discussed, there are 3 sources of error in learning that we have to think about. First of all, there's approximation error. So if your function class is too small, so that the true function that you're trying to estimate is far outside of this class, you'll have a high approximation error. So this suggests that you want to have a large function class. On the other hand, there's statistical error, which means that given a finite sample, you're going to likely not find the true function. There's going to be some kind of error. And this kind of error will grow as you grow your function class. So from that perspective, you'd like to have a small function class. And finally, there's optimization error, which relates to how well you can actually find the optimal hypothesis in your hypothesis class with some data. And although that is a very important and interesting topic, we're not going to discuss it in detail today. It seems, although this is not fully understood, it seems like actually many deep networks, although the loss functions aren't convex, we can actually solve this optimization problem quite well. Now, what we're going to do with these geometric priors is that by using geometric priors, for instance, by using equivariant networks that respect the symmetries of our problem, we can decrease the size or complexity of this hypothesis class. For instance, only admit equivariant neural nets, which will decrease the statistical error, hopefully. Smaller hypothesis class, smaller statistical error, less risk of overfitting. And hopefully, it'll do that without discarding useful hypotheses. So if we know for sure that the true function we're trying to approximate respects to symmetry is equivariant, then limiting to equivariant functions would not increase the approximation error, and at least not if our function class is a universal approximator of equivariant functions. Okay, so let's look at these geometric domains. So in geometric deep learning, the data always, I think I don't know any other example where it's not true, basically always lives on a domain that we will denote by omega. So some examples are grids, groups, graphs, and manifolds, where you deal with geodesics and gauges. You know, we couldn't use manifolds because it's not doesn't start with a G, so that's why we have these. The domain is always a set. That's typical in mathematics. Your domain is some kind of set, but it may have different kind of structure. So, for instance, in the case of a grid, you might think of that as having neighborhood structure, just like in a graph. You can say which nodes are connected to which nodes, and you might also endow it with really a metric structure, saying what is the distance between points. The same you can do on a manifold like this sphere or this human figure. You can measure the distance of points along the surface. That's part of the structure. So the key message of geometric deep learning is that we want to design neural networks for processing geometric data. If we want to do that, those networks should respect the structure of the domain, whatever the structure may be, and there are many choices. And as we will show in this course, many of the popular architectures, although it's not always described in this way, they implicitly assume a certain structure in the domain, and then these networks actually respect that structure, and that's one of the reasons why they work well. All right, so we've discussed the geometric domains, and we've seen a couple of examples on it, but most of the time the data is not a domain itself. Our data isn't a grid, it's a signal on the grid or a signal on some other space. So what's a signal? Well, a signal essentially is just a function. We typically denote it by x. It's a function that takes as input an element of our domain omega, and it outputs a vector in some vector space C, where the dimensions of C are typically called channels. So simplest and most common example is where our domain is a grid. So we can mathematically describe that as Zn times Zn, Zn being the set of integers 0 up to n minus 1. And the Cartesian product gives you a grid. And a signal is described as a function taking some grid point and mapping it to R3, a space of RGB values. Similarly, we can do the same for a graph. So here we have a molecular graph where now our domain is this set of nodes, which we could, for instance, label by the numbers 1 through n. And in this example, if we just ignore the geometrical positions, we could say that this molecule is described as a function from this graph to the set of, to a vector space of dimension m, where m is the number of atoms that we care about in this problem. So there might be carbon atoms, nitrogen, oxygen, and for each node in the graph, each atom, you assign a one-hot vector that tells you which kind of atom this is. So we then have the space of C-valued signals on omega, and that's just, well, the set of all functions of this signature, all kinds of signals on this space. Sometimes you'll want to include some regularity conditions as well, but we won't go into that here. So that's our data space. It's denoted by this script x, and sometimes we'll indicate the domain and the space of channels, so omega and C. Sometimes we'll leave that out if it's clear, but X is the data space. Now this space of signals has interesting structure. So if we think about the domain could be a vector space. For instance, if you have a continuous planar continuous plane R2 could be the domain that you use to model images. There you can add points. But if you have, say, a graph, we don't have any notion of addition of nodes in a graph. And nevertheless, the space of signals will always have a vector space structure. That is to say, we can always add two signals, and we can always multiply signals by a scalar. So mathematically, this is described by the equation that we have here. We have two signals, x and y, shown here as the two images, these two squares. And we have scalars, alpha and beta, real numbers. And then we can form the signal alpha x plus beta y. We can evaluate it at a point u, that's a point in the plane. And this addition is just defined pointwise. So we evaluate the first function at u and the second function y at u, and we linearly combine these numbers with alpha and beta and adding them. And the result is just a composition of these two images, as you see in the figure. All right, so this means that the space of signals is a vector space. If the domain itself has an infinite number of points, then this will be an infinite dimensional vector space, but a vector space nonetheless. And of course, whenever we're actually doing computations, we're going to have to work with something finite. Now, there's more, because this vector space, we can typically also make it into an inner product space or a Hilbert space, if you want to use a fancy name. So to define this, we need two ingredients. First of all, we need to start with an inner product on the space of channels. So that's typically very easy. The channels is typically finite dimensional vector space Rn. So we can just use a standard inner product there. And we also need something, namely a measure on omega. And a measure is something that allows you to essentially, measure the size of sets, subsets of omega. And using that kind of structure, you can define an integral. We can then define an inner product on signals, the inner product between x and y, as the integral over omega of the inner product between the feature vector at u of x and the feature vector of at u of y, where this integral is defined with respect to this measure. Now that's a whole lot of complicated mathematical setup that we have here, but in most cases it boils down to something pretty simple. So in particular, if omega is a finite set, then you can use something called a counting measure, in which case the integral just becomes a sum over omega. And in that case, I think you can quite easily recognize that this equation here looks like an inner product on a finite dimensional vector space, because we're summing over the points of omega, just like you're summing over the dimensions of a vector space when you do an inner product. And what are we summing? Well, we're summing a product, in this case, inner product of the feature vectors. And you can check that this indeed satisfies the actions of an inner product. And the reason we need this is that we want to do pattern matching, right? When we do a linear layer, when we do a convolution, we somehow need to compare our signal x to some kind of filter y. All right, so conclusion, the space of signals is a Hilbert space, as long as we can define these two ingredients, inner product on C and a measure mu. All right, then there's another layer of subtlety. We won't really be using this in this lecture, but I think it's important to at least be aware of this. So far what I've said is that a signal is a function on omega. So what does a function do? Well, it takes an element u of omega and it maps it to some element x of u in C. For every pixel, it assigns an RGB vector, for example. Now there's something slightly more general, which is called a field in physics, or in mathematics, it's called a section of a bundle, of a vector bundle, to be precise. And this is a slight generalization of a function where instead of mapping u in omega to some xu in a fixed space C, you're mapping it to an element of a vector space C that's indexed by U. So to make that more intuitive, we can look at this figure here of a vector field on a mesh. So a vector field assigns to each point in the manifold a vector, and this vector lies in the tangent plane to that point. So every point on the manifold has a tangent plane. You can see that drawn here on the sphere. The best linear approximation of the manifold is one way to think about it. And the vector of the vector assigned to the point U has to lie in that tangent plane, but there's a different tangent plane for every point. So essentially, you're mapping to a different space. So this can be modeled using the theory of fiber bundles, but as I mentioned, we're not going to talk too much about that. Just good to be aware of that. So in some cases, so far I've said that the data are signals on our domain. There are some cases where actually the domain itself is the data. So one example would be a mesh. So you can think of your mesh is a domain, but we just want to process the mesh itself. Another example could be point clouds, where each point just has a position in space and no other associated features. So to deal with this, there are some tricks people like to use, such as, for example, using the graph adjacency matrix. So the matrix with n of size n by n, where n is the number of nodes, where you have an entry 1 in position ij if node I is connected to node j, and 0 otherwise. And you can think of that as a signal on omega times omega, so the space of pairs of nodes in your graph. If you have a manifold or a mesh, you can use something called the metric tensor, and this is an intrinsic quantity associated with the mesh. You can view that as a signal. So there are ways to turn the domain into a signal on the domain in some cases. Okay, so now we get to the core of this lecture. We're going to talk about symmetries. So what's a symmetry? Well, here's a simple definition. A symmetry of an object is a transformation of that object that leaves it unchanged. So here's a very visual, intuitive example. If our object here being referred to is a triangle, we can do certain transformations to the triangle that don't change it. So we could rotate it by 2 pi over 3, and that will just place every point in the triangle onto another point in the triangle, and the shape overall is unchanged. We can also flip it horizontal let's say in a vertical line, and again it doesn't change the object. So we're going to talk about these kinds of diagrams in a second, but what you see already is that we have here 6 possible configurations of the triangle, and they're related to these transformations, these symmetries. They can be somehow composed. For instance, we can start at the top and apply a rotation, another rotation, and another one, and we get back to where we started. This is this somehow signifies the structure of this set of symmetries called a group. All right. So symmetry. So here we have a very visual example, right? This is intuitive. We're all familiar with symmetry of this kind, but in mathematics, in physics, and also in geometric deep learning, the word symmetry takes on a slightly more abstract meaning, because this word object that we have here in our definition can also be interpreted in a much more abstract way. So we're going to look at a couple of examples of how symmetries appear in machine learning. So the first one is actually not going to be a focus of this lecture, but it's interesting to know about, I think. This is what we call symmetries of the parameterization. So we have a couple of ingredients. We have, again, our input space X. This could be a space of signals, but for this slide, it doesn't matter what it is. It's some vector space X. We have some output space Y, say a space of labels. And we have a space W of weights or parameters. Then we have a model, typically, let's say, a neural network that maps an input point and a weight vector to a label. Then we would say that a transformation G, which maps the weight space to itself, is a symmetry of the parameterization if this equation holds. If it is the case that if we apply G to our weight vector and then do a feed forward pass using this input X, we get the same as if we did the forward pass using the original weights. So one example of how this happens is if we have a neural network. Here's a very small, simple network, and we could swap the nodes and their associated incoming and outgoing connections. We can permute them for the neurons within a single layer, and you can see that this will leave the result unchanged because of the the final outputs are computed by adding over all the input connections, and then the order of the inputs doesn't matter. So you can permute the internal the hidden units, and it won't change the function being learned. Now this could be relevant if, for example, you're doing something like Bayesian inference. If you're doing Bayesian inference, you might have a prior over your weight space. You might say, I think this kind of weight vector is more likely than this one. But if those two weight vectors actually specify the same function, it doesn't really make sense to say one is more likely than the other. So you might want to deal with that symmetry. It's not something widely appreciated at this point, but I think it might be relevant. Then we get to another kind of symmetry as it appears in machine learning. This is a symmetry of the label function. This is what we'll be talking about mostly today. So again, we have X, our data, our input space, and Y, our output space. And now we consider the label function, the true function that we're trying to approximate, which maps inputs to outputs, to labels. And then we have a transformation G. Now it doesn't act on the weight space, but it acts on the input space. So for example, as shown on the bottom, G could be a rotation of the image. And we will say that G is a symmetry of the label function if, remember the definition, if it leaves this thing unchanged. So if we precompose L with G, that is to say we first apply transformation and then we compute the label, that should be the same as just computing the label right away. If this holds, we say G is a symmetry of this label function. So we know many symmetries like this in the problems like computer vision, rotating, translating images, scaling them, etc. Typically doesn't change the label. Now, it turns out that actually you can think of all learning as, or at least all supervised learning as learning about symmetries. So what we see here is our input space X, that's the gray set. And let's say we have two classes with the two different colors. And within these classes live a bunch of points. Those are the possible inputs. Now you can see that any invertible map on this space X that respects the class boundaries, meaning it maps a point in a certain class to another point in that class, will be a symmetry of the label function. So if we knew all the symmetries of our label function L, then we would effectively know these classes because we could start at one point and we could apply one symmetry a bunch of times and maybe another symmetry and so on, and we would reach every other point in that same class. And so in this way, we can learn that all of these points should have the same label. And so at least up to permutation of the classes, up to actually figure out what label belongs to each of these two sets in this case, we've solved the problem if we know all the symmetries. So that tells us something. First of all, it's kind of an interesting way to think about learning, but it also tells us that if our learning problem is non-trivial, that is to say, if we actually believe we need learning to solve this problem, we can't hand code it, then we should also not expect that a priori we can know all the symmetries, because it's essentially equivalent to knowing the label function, at least up to a permutation of the classes. So if we can't know all of the symmetries of our label function a priori, what are we going to do? Well, it turns out that at least in a large class of problems, the ones that we refer to as geometric deep learning problems, there's a source of symmetries that comes from the domain on which the data lives. So here we are again, we have our domain omega, and we say that a transformation G of this space omega is a symmetry of omega if it preserves the structure of omega. So that is deliberately vague. You could, using very abstract mathematics, make precise what we mean by structure. But for now, I'll just give a bunch of examples. So if our domain is just a set, then what is the structure of a set? Well, set membership is all you can say. You can only say whether an element is part of the set or not. Nothing about the order, nothing about the relation between different elements in the set. And so a permutation of the elements of a set preserves the structure here. If we have a Euclidean space, such as omega equal to r to the d, let's say a plane, and let's say we consider this not just as a manifold, but we consider it as a metric space. So we think the distance between points is part of the structure of this space. Then the symmetries would be Euclidean isometries, i.e. Distance preserving maps. Things like translation, rotation, reflection, you can easily visualize and see that these don't change the distances between points. If, on the other hand, we consider R2 or really any manifold only as a smooth manifold, so we don't endow it with a metric, then any kind of diffeomorphism, any kind of sort of smooth warping of the domain can be considered a symmetry. So what's a symmetry depends on what you define exactly to be the structure of your domain omega. Now, we can observe a couple things about symmetries. What we're going to do is we're going to consider this, a single object or single domain, let's say, and then we consider the set of all symmetries of this object. So we can observe a couple things about this set. First of all, we observe that the identity transformation is always a symmetry. If we don't change anything, of course, nothing changes. Then we can see that given two symmetry transformations, their composition, so doing one after the other, is also a symmetry. So if we think about the triangle again, for instance, we rotate it by 2 pi over 3. That leaves the triangle invariant. If we do it again, that still leaves the invariant. So the rotation by 2 times 2 pi over 3 is also a symmetry. So composition of symmetries is a symmetry. So it's also in the set of all symmetries of the object. And finally, given any symmetry, its inverse is also a symmetry. If we have as object our grid, if we shift it one way and when we shift it back, clearly both of those are symmetries. So we can formalize this, and the object that formalizes these properties is called a group. We will denote it with this factor letter G. So a group is a set G with a binary operation, which we just denote by putting one letter after the other, juxtaposition, satisfying the following properties. So first of all, associativity, that the order of multiplication or where you put the brackets is irrelevant. In either case, if we have G, H, and L, this means first do L, then H, then G. Identity, so this is our first observation on the previous slide. Every symmetry group has to have a unique element E in the group that satisfies this equation. If we do any transformation followed by the identity, or it's the same as doing the identity followed by that transformation, is the same as just doing that transformation. And inverses, so meaning that for every element G, there exists a unique inverse which satisfies the equation for an inverse. and closure. So for every pair G and H in our group, the composition or the group product applied to these two elements is also an element of the group. So this is essentially an abstraction of the set of all symmetries of any given object. So it's good to keep this a couple different notions straight. So first we have this idea of a symmetry group. A common way to define that is to say a symmetry group is a group whose elements are actually transformations, they're functions of some domain. And then the group operation is the composition of maps. You know, you learn this when you study functions, you know how to compose maps, and this is always associative. This is one natural way to define a group operation. But in the abstract study of groups, which you might run into when you look at some mathematical text, the elements of the group are not assumed to be functions. They're just elements of a set. And we have some synthetic composition rule that satisfies the group action. The group actions. And then finally, if you use that approach, you can define something called a group action, which is a function that takes a group element and an element of the domain omega and maps it to a new element of the domain omega, satisfying certain natural axioms. But regardless, we'll mostly be thinking about the concrete case of symmetry groups, where we think of our group elements as functions. So here's a simple example of a group action. So we can take the example of the Euclidean group. So an element of this of the Euclidean group in 2 dimensions has a rotation component. Let's say we code it as an angle theta, and a translation component in the x and y direction. And we apply it to a 2-dimensional point, x, y. Well, one way to do it is to form this matrix, which has a rotation matrix here and a translation part here, and apply it to this vector to produce the rotated and translated version of this point. Yeah, and it's a nice exercise to verify that this indeed satisfies the axioms of a group action. All right, so if our group is finite and discrete, there's 2 nice ways that we can think about the structure of this group. So here again, we have this figure for the group of symmetries of a triangle. And this kind of figure is called a Cayley diagram. So every node in this diagram is some configuration of the object, but we can also identify it with a group element. So if we take this top element and we identify it with the identity element, we say this is sort of the canonical orientation of this object. Then we can take, for example, the rotation group element and apply it to the triangle, and we get to the rotated triangle, which as a triangle is unchanged, although the corners, as you can see, get permuted. And so we might also associate this triangle here with the rotation element R. We can apply it again, and we get to the element R squared, R times R, which is an element of our group, and so on, and we get back to the identity. And you can see how these transformations compose in an interesting way. So for example, if we start at the identity and we flip and then rotate, we end up here. If on the other hand, we first rotate, let's see, I think actually there's a mistake in this diagram, yeah. Sorry about that. So for this group, it should be the case that if you flip and then rotate, you end up here. Whereas if you first rotate and then flip, you end up in a different position. This shows the non-commutative nature of this group. I hope I'm not making any mistakes here, but you see the structure of the group reflected in the diagram. Another way to think about the structure of the group is via this multiplication table. So what we have here is in the rows, we have every element of the group, and also in the column again we have every element of the group. And looking at any any entry in the interior of this table, we see what you get if you multiply two of these things. So for example, if we have a rotation and the rotation done twice, we multiply them, we get to the identity. So that makes sense, right? That's this rotate, rotate, and rotate, you get back to where you started. All right, so this is a nice way to get some intuitive understanding of finite groups, but there are actually many kinds of groups, and most of them are not finite and not even discrete in some cases. So very broadly, we can divide groups into two kinds. We can think about discrete groups and continuous groups, and maybe even differential or Lie groups. So in the discrete group, you could have finite groups like this group of, let's say, rotational symmetries of the triangle, or rotation and reflection symmetries that we looked at on the last slide. And the set of discrete groups also includes infinite ones, like countably infinite discrete groups, such as translations of the set of integers, or the infinitely extended grid is Z by Z. Continuous groups can be divided into compact groups, things like two-dimensional rotations, and so-called locally compact groups, such as continuous translations or roto-translations, R to the D or SE, and special Euclidean rotation translations. There are even non-locally compact groups, which are intuitively, you can think of it as well, I'm not going to try to define that, but there's, for instance, this infinitely dimensional group of diffeomorphisms, which are sort of the hardest to get a mathematical handle on. And for all of the above cases, you can think about commutative cases, like the group of two-dimensional rotations in 2 dimensions, where the order doesn't matter, or non-commutative ones, such as rotations in 3 dimensions. Where the order does matter. All right, so as I mentioned, symmetries acting on our domain omega will also immediately act on the space of signals on omega. This is defined via this equation. So we have our signal x, and we have an element g. We define here a new group action of g on signals x. And this transformed signal, if we evaluate it at a point u in the domain, it's equal to the original signal x evaluated at g inverse u. So please excuse the hand-drawn figure. We're still working on this book and working on better figures. But what this signifies is that we have our group, and we start off with a group action on the domain, which could be grid, a sphere, a graph, manifold, etc. And from there, we get an action on the space of signals. So let's look at an example translating an image. So here G is a translation with some X and Y component. We have here our image. This is the on the right. We have here our original image, and we see that this bug is going to move from the left-hand side of the image to the right-hand side. So that's t is some positive number, translating along the x direction. And to get the value of the translated image gx at the point u, which is somewhere, let's say, on this bug, what we have to do is we have to look in the original image at the point u minus t to see what the value was there. Because this value u minus, or this point u minus t, is going to translate to the point u if we apply transformation t. Another reason why we have this inverse, so in this case the minus, and in the previous equation here we have this g inverse, is that without it, you wouldn't satisfy the actions of the axioms of a group action. And that is another exercise that you can try to show that with this definition here, we get a valid group action that is associative. Now, one interesting observation is that again, whereas the domain may not have any kind of vector space structure, the space of signals always has a vector space structure. And this group action that we just defined is actually linear in the signal. So here we have, I've repeated the definition of our group action on signals. And here I've written the condition for linearity. So what this means is if we have some linear combination of signals and there we apply our transformation G to that, that should be the same as applying G to the individual signals and then linearly combining those signals. And so here we see that we have one signal, another signal, and their addition. And if we now go to the bottom of the figure, we apply a translation, in this case, vertical translation. We see that, well, applying this vertical translation, and then adding is the same as first adding the images on the top and then translating the resulting image. So you see that action on signals is linear. Now, linear group actions are also known as group representations. So here's the definition. An n-dimensional real representation of some group G is a mapping row that takes an element of our group G and maps it to an n by n matrix in the case of at least a finite n-dimensional vector space. And so this assigns a matrix. This matrix is always invertible by definition, and it has to satisfy this kind of homomorphism property, as it's called. You can check again that the definition I just gave for how the group acts on the space of signals satisfies this, this condition. So that's a group representation. So here's a simple example. Our group could be the set of integer translations in one dimension, so +1, +2, or -5, these kinds of things. The group operation is given by plus, by the addition of integers. As our domain, we can take the set Z5, 0, 1, 2, 3, 4. Maybe this is, well, it's artificially short, but it could be some audio signal, for example, domain of, or the sample points of an audio signal. And we have an action over group G, where now the elements of this group G are integers n. We have an action on omega that sends each point to that point plus n mod 5. So we have sort of a cyclic shifting operation here. And then the representation on signals on omega. So first of all, this space is a 5-dimensional space because we have, in this case, 5 sample points in our domain. So it's a 5 by 5 matrix. And here it is again. We saw it in the first lecture. It's the shift operator. And if we want to do, represent the element n, we would take the shift operator and take it to the nth matrix power. And the way it acts on our signal is if we have a 5-dimensional vector, we apply, let's say, row 1, and it performs a cyclic shift on those values. So the important thing here to notice is that our group may have some number of elements, in this case, infinite. Sometimes it's a finite group. Sometimes it's a continuous group with a certain number of dimensions. But this is completely independent, the size and structure of the group, of the dimension of the representation. The dimension of the representation is the dimension of our feature space that it's acting on. So we can look at a couple examples of symmetries for the different G's. So in the case of sets and graphs, the group is the symmetric group, not to be confused with symmetry group. It's a symmetric group, the group of permutations on n elements. The domain could be the set of nodes or vertices, or possibly also the set of edges. And we can distinguish 3 kinds of graph features, each one corresponding to a different representation of this symmetric group Sn. So first of all, if let's say we're classifying a graph, then for the output, we will have one number. And clearly, if we permute the nodes of the graph, it's still the same graph. So we want that to not change. And so this can be captured by choosing for the output space the something called the trivial representation. So the trivial representation row 0, if we give it some permutation, say permutation that swaps the first and second element of the set of nodes, and we apply it to S. That's a vector in our space of signals, in this case, a one-dimensional vector. Nothing happens. So you can check that this trivial representation still satisfies the axioms of a representation, and this is what you want the output space to transform like. Then if you have some features associated with the nodes, let's say here we have a graph with 4 nodes, so we have four-dimensional signal, then the representation row 1 of this permutation is just this permutation matrix applied to our vector of node features. And finally, if we have edge features, or let's say an adjacency matrix or something like this, we would use something called a tensor feature, where the representation row 2 of this permutation acts on a matrix M in this way. And again, you can check that the axioms of a group representation are satisfied. Now, one important thing to realize is that there are really 2 kinds of symmetries at play here. So first note that a graph, or even just a set, is actually an abstract object. What we have in our computer is just a sequence. It's essentially a description of the set, but it has some extraneous properties like the order of the elements of the set, or the nodes of the graph. And usually we're interested in the symmetries of this description rather than the symmetries of the object itself. So to explain that a bit, I have this graph here. And if we choose labels for the nodes, if we choose an ordering, we can write this graph as an adjacency matrix like this. The ijth entry says that has a 1 if node I and j are linked by an edge. Then if we apply some permutation, we'll permute the rows and the columns of this matrix, and we get a different matrix. So this is a symmetry of the description. We have here a different description of the same graph. That's what we want our network to be invariant or equivariant to. But you can also see that this graph itself has some kind of symmetry. So if we do another permutation where we just swap node 3 and 4, both of which sort of play the same role in this graph, you see actually that the representation doesn't change. The adjacency matrix is the same. So that's another way, another notion of symmetry here. That's a symmetry of this particular instance rather than our way of encoding graphs. It's good to keep those straight. All right, for grids, we have as groups, discrete translations, rotations, flips. The domain is the set of grid points, not shown in the diagram, but you know what we mean. And our representation is a regular representation, so we could shift and rotate this image like this. These cases can be generalized to the setting of general groups and homogeneous spaces, which we'll cover in lecture 8. So there G is could be essentially any group. Typically, we choose it locally compact. And we have a space called a homogeneous space, which means that for any 2 points in this space, there's at least one symmetry that maps one point into the other. For these cases, we can give a very general, general theory of equivariant nets. And finally, there's manifolds or geodesics and gauges, if you want to stick with the 5G theme. So here the group G is the group of gauge transformations, which refers to changes in the reference frames of these feature spaces. So here we have again our vector field. Remember, a vector field assigns to each point in the manifold a vector in the tangent plane at that point. But to represent such a vector numerically, you need to choose a frame in the tangent plane. And changing this frame will change the numerical representation of your data. So that's called a gauge transformation, because, we'll cover that in one of the later lectures. So I'm running a bit short on time, so I'm actually going to skip this slide. We're going to talk about invariance and equivariance. So let's say we have symmetry of the label function. Here we're trying to classify letters A and B. The letters might appear in different fonts and also different orientations. So we have our symmetry corresponding to rotations of the digits. And clearly, if we know that this is a symmetry of the label function, then it would be nice if we can form some invariant representation where each of the rotated versions of the same letter is represented by one kind of feature vector. Then our problem becomes easier. You can see here we only have 4 points in our space, whereas here we have 4 times 4 points. So the learning problem should become easier if we have an invariant representation. However, in deep learning, it's often not a good idea to build an invariant representation, at least not too soon. So the reason is the following. So to recognize a whole object, we first need to recognize the parts of that object. But if we make the intermediate representations, the representations of the parts, if we make those invariant, we will lose some critical information. So if we have an image and we rotate the whole image, then this identity is preserved. But if we rotate the parts, clearly this is no longer a correct face because the parts are in the wrong relative spatial configuration. So if we were to form a representation of this image of the that is invariant, has an invariant representation of each of the parts. So we have here, we detect an eye regardless of its orientation, a nose here regardless of the orientation, etc. Then this kind of image would yield the same representation. We just rotated each part, but clearly something is wrong about this. It's no longer a proper face. So we want to exploit the symmetry, but we don't want to make an invariant representation of the parts. And to make an invariant representation of the whole, we first need to recognize the parts. So what are we gonna do? Well, the solution, as many have noted, is to use equivariate networks. So here's the general setup for an equivariant network. We have our feature spaces, x0, that's the input space. We have x1, x2, x3, and so on. And we have network layers, F1, F2, F3. They could be linear layers, convolutions, nonlinearities, etc. And in an equivariate network, there's a couple extra ingredients beyond what you have in a normal neural network. Namely, first of all, there's a symmetry group. And secondly, for each feature space, I, there is a representation rho I of that feature space that acts on it. So the simplest example might be a planar image, and you have, let's say, an RGB input. So we have n by n pixels and 3 channels. So our feature space X is n by n by 3. So we have an n by n by 3-dimensional representation of our group G, which could be translations. And maybe our X1 is the output of a convolution layer with 64 channels. And so now our feature space is n by n by 64 dimensional. So that's a different representation of the same group G of translations. And we say that the network is equivariant if this equation is satisfied, if we, which you can also understand from this diagram. If we start, say, here at x0, we apply a transformation using rho 0. Let's say we shift the image and then apply the first layer. We should get the same thing as if we first applied the first layer and then applied the same transformation, but now acting via the representation that we have in the feature space to produce x1. These two things should be the same, give the same result. If F1 and F2 and all of the layers of the network satisfy this property, then we say the network is equivariant, and you can show that if each layer satisfies equivariance, then also their composition satisfies this, i.e. is equivariant. So here's what it looks like. A convolution layer is translation equivariant. I think we're all familiar with that. A convolution is a standard convolutional network is not rotation equivariant. So that's visualized here. We have an image undergoing rotation, and here's a feature map produced by the network. And it seems maybe at first sight to be rotating a little bit, but it's also morphing in some weird ways. And that we see if we stabilize this feature map, i.e. if we undo the rotation in the feature space, we see that this thing is changing. So this neuron is detecting different things depending on the orientation. Maybe in one orientation, it likes to detect grass, and in another orientation, it likes to detect building or something like this. In a GCNN, a rotation equivariant convolutional net, you can see that that the feature map actually does undergo a rotation, and stabilized view is invariant. So here's one way that we can understand equivariance. We have again here our equation, and we have again our problem of classifying digits. Now on the bottom here we see our input space with two marked points x and y. There are two signals, and they lie on what's called an orbit. So if we take this letter A, and we consider all the rotated copies of that letter, that will form some manifold called the orbit of this letter. And in particular, there's another point, rho 1g of x, which corresponds to this particular rotated version of the A, and similarly for y. Now we also have our network, which maps this input to some feature vector. This feature vector here is symbolized by this generic letter A, because we assume in this example that the network has learned that it's a good idea to map X, this letter, and Y, this other font of the same letter A, to this generic A, because it should classify the digit regardless of the font. So these are the same. Now in a non-equivariant network, it could be that for the rotated versions of these letters, they actually get sent to different points in the feature space by our network. But you can see that if this were the case, the network could not possibly be equivariant, because we must have that if we take X and transform X and then apply our layer, we should get the same as applying our layer and then transforming. But the same should be true for Y. We transform and we get to a different point. But if we first apply our layer, we get to the same point as X is mapped to. So it's unclear where row 2 should be sending this generic letter A. So another way to phrase that is that an equivariant network must generalize in a way that's consistent with the symmetry. If we think X and Y should be mapped to the same points, then also their transformed versions should be mapped to the same points. I often get asked about, why not use data augmentation? Of course, data augmentation is very widely used, and it's easy, so it's very popular, but there are various advantages and disadvantages. The most important argument, I think, in favor of equivariance is that in certain problems where you really have symmetries, like say medical image segmentation, let's say histopathology slides, you really have a translation and a rotation symmetry. In those cases, we actually see that equivariant nets just get way better performance. They get up to 10 times better data efficiency. And so why could that be? Well, one potential explanation is that an equivariance constraint acts in a layer-wise fashion, whereas data augmentation is something that constrains the network as a whole. The downside is that equivariant nets, you actually need to think about how to implement it. Depending on the particular method, it can be very complicated or just a little bit extra work, whereas augmentation tends to be very easy. I should say that there's, of course, train time augmentation, the most common, where you augment training data as you're training. And there's test time augmentation, where you take a test image or test input and you apply all possible transformations, you feed them all forward through your network, and then you average the results. This approach gives you guaranteed equivariance for test time augmentation and also for equivariant networks. But train time augmentation does not, and you can actually verify this. You can test a network trained with data augmentation, and you will see it's typically not equivariant. This probably has to do with the fact that you cannot show every possible input combined with every possible transformation to the network during training. Maybe in the interest of time, I'll go quickly. So for one other downside of augmentation is that it just doesn't work for very large groups. So if you have a graph with n nodes, n being large, the symmetry group Sn has a factorial number of elements. And so it's totally impossible to sample every permutation, not during training, and certainly not all of them for every test image. So In this case, yeah, everybody uses graph networks that are equivariant because it's just completely infeasible to use augmentation. All right, so I'm going to skip this. I'll make a quick comment about this, which is that there's some interesting research, for instance, from the Clarity team at OpenAI, that has found that conventional networks, typically trained with the data augmentation, actually learn to be equivariant, at least to some degree. And interestingly, the way that these networks implement the equivariance in their weights is the same as what the theory, which I haven't covered yet, but the theory of group equivariant convolutional nets suggests for how to implement this. So that's some interesting background reading if you're curious. All right, to summarize this lecture, symmetries are transformations that leave some object invariant. There's this notion of group, which formalizes the properties of the set of all symmetries of an object. A couple axioms like associative, activity, identity, closure under composition, and closure under inverses. In machine learning, we care about symmetries of the parameterization, and most of all about symmetries of label function, and particularly the symmetries of the label function that arise from the symmetries of the domain. These symmetries that of the domain, they act linearly on the space of signals via something called a group representation. And to exploit symmetry in deep learning, we use equivariant networks. In an equivariant network, each feature space is associated with a group representation, telling you how the group acts on this feature space. And each layer is equivariant with respect to these representations. Now, invariance is a special case where the trivial representation is used. All right, that's it, and I'm happy to take questions.